Problem number 107, chapter 23, OpenStax College Physics, 2nd edition. This problem is a little strange, but I wanted to try it because it seemed interesting. It says, let's build a magnetic field detector. So we're going to build this detector. We have 4 meters of wire. I'm going to stand right here. We have 4 meters of wire, and we make that into a square. So we can calculate the dimensions of that square. I mean, it's 1 by 1 by 1, right? Obviously, because the perimeter is 4. And let's say the magnetic field is actually 0.02 Tesla. And the coil is rotated, okay? So if it's rotated, then we're changing that angle between theta and the area, so we will induce an EMF. The first question says that, what's the average EMF over a quarter of a cycle? So let's just stop for a second. Remember that Faraday's law says that the EMF is negative in change in flux with respect to time. The negative sign is part of Lenz's law. We don't have to worry about that. N is the number of loops. So here we only have 1 loop. And flux is BA cosine theta. So let's imagine that this coil, if it goes through a full rotation, I need a square. How about just use this piece of paper? Okay, so there's my square right there. Let's imagine I have that square, and the magnetic field is this way, coming out of the board. So I'm going to pick that. So this is my magnetic field. So 1 full rotation would be all the way around like that. That's 1. So a half rotation would be like this, and a quarter rotation would be easy. It's just going from here to there. Okay. Now, how long would that take? Well, the time, let's just write this as delta t, would be, it'd be a fourth of the time to go all the way around. But the time to go all the way around is 1 over 400. So this is going to be 1/4, 1 over 400. Right? 1 over 400 is the time for 1 oscillation, 1 rotation, and we're only going a quarter of that. So that's our time. Okay. Now, what about the flux? I know B, A, is going to be W squared, which is 1 times 1 meter squared. And theta, so let's just write this as EMF is going to be equal to, I'm going to leave off the negative sign because it doesn't matter, N is 1. I'm going to have flux 2 minus flux 1 over delta t. So here I have the flux where the angle between the area and the magnetic field is 0, right? Because the area is this way and the magnetic field is the same way. When I rotate a quarter of a turn like that, now my area angle is that way, but the magnetic field is still this way. The angle between those is 0. So this goes to 0 because cosine of 90 is 0. So I have 0 minus the magnetic field times the area times cosine of 1, or cosine of 0, which is 1, over delta t. And again, I don't care about the sign. So that will be my average EMF. Let's put it all together. EMF is going to be B 0.02 times the area, which is 1 squared, divided by delta t, which is 1 over that. So it's actually 4 times 400. Calculator time. I like to hold up my calculator just so you know it's real. 0.02, enter. 1 squared, I'm going to just do that in my head. 4 times 400 times. I get 32 volts. So let's put that over here. 32 volts. Okay. Now, the next question says, imagine that I take that same loop of wire and I make 2 coils, right? So N is going to be equal to 2. But if I do that, my area is going to be less. So in fact, I'm going to have my total perimeter is going to be 2 of each square. So here, I'm going to get, if the perimeter is 2, this is going to be 0.5 by 0.5. So I can redo the problem. The only thing I'm going to change is n and a. So I'm going to multiply this by n, like that. That's the only thing I need to change. So let's just do the calculations. I'm going to put the 2 right here. This is the magnetic field, that's fine. This is the area. Now it's not 1 squared, it's going to be 0.5 squared. 0.5 squared. And then that's the same, that's the same. So we can just recalculate this whole thing with my calculator. Drop. 2 enter 0.02 times 0.5 squared times 4 times 400 times. And I get 16 volts. So in this case, notice that by making the area half, I made the perimeter half as much. If I make the perimeter half as much, my area is 1/4 as much, right? Because if I make these both half as much, when I square it, that's 1/4. That's 1/4 as much. But I have 2 of them. So I have 2 times 1/4, which is 1/2. So I have half the effective area, so it's going to be half the EMF. Okay. Now, this last question, part C, is a little weird. I don't really know how to answer it. Because it says, what if it's in a figure 8? Okay. So what if, I'm thinking a square figure 8. Like that. And that's a terrible figure 8. But the problem is, does the orientation of the loop change? Right? If I did a figure 8 and I twisted it and the direction of the orientation was one way here and the other way here, even if they're the same area, the induced EMF right here and the induced EMF right here would be completely opposite, and you'd get 0 flux. You'd get 0 change in flux. You'd get 0 flux, right? Because the two areas are oppositely oriented. Now, if you make it so that they're both going in the same orientation, which I'm not exactly sure how you do that, if I have the wire go up here, see, it'd be opposite. I think it'd have to be no matter what. Even if you do a normal figure 8 like that. Well, if you do a cross like that, you could twist this one over, and you could do this. That would be fine. But then remember, the thing is you want to maximize the area, not the perimeter. And this is you're wasting a lot of that wire on the area, on the perimeter, but you're not really increasing the area. So flux depends on the area, not the perimeter. So this would be a lower voltage than the other case. So it wouldn't be as good. And in fact, the best case is this, a circle. Because that has the lowest perimeter to area ratio, I'm pretty sure. Pi r squared, yeah. Making it multiple loops with the same wire, multiple loops helps, but not if you have to sacrifice wire. Okay. So I told you that was a weird part C. I didn't really do any calculation. The shape only matters. The question was, does the shape matter? The shape matters only in that different shapes have lower areas. Area is what matters.